Hello, everybody. Welcome to the lecture for today, April 20th. Today, we're going to be continuing our discussion about Lie groups. Just groups in general. Lie groups is too advanced of a topic, but we're going to hopefully prove one theorem today. If we don't prove it today, we'll prove it on Wednesday, which is Lagrange's theorem, which is sort of the main generalization of the theorem that we want to prove, that we proved before, called Fermat's theorem or Euler's theorem. And we'll see how we can get both Fermat's and Euler's theorem as a corollary of Lagrange's theorem, probably on Wednesday. We won't get to the corollary today, or see how it links. But to be able to discuss Lagrange's theorem, we need some new definitions. And the first definition is something we already know. It's the cardinality, but when we talk about groups, we usually use a different word. And that word is called order. So if you have a group, the order of a group is its cardinality. So if the group is finite, the order is just the number of elements that the group has. So for instance, the integers have order infinity because their cardinality is infinity. The group Zn with addition has order n because there are n distinct congruence classes, mod n. And the symmetric group has n factorial elements. The number of ways to reorder n things is n factorial. So the order of the symmetric group Sn is n factorial. Okay, so how do we want to think about order, and why do we care about order? Well, it allows us to put restrictions on what can be a subgroup. Subgroups will have to satisfy certain properties of their order. In particular, they have to satisfy certain divisibility properties related to the order of the group G. And that's what Lagrange's theorem will be about. So to get there, we need to first define something called a coset. And before we define what a coset is, I just want to recall some structures from our study of the integers to see how it relates to the study of groups. So the first thing to note is that all of the multiples of, if you fix a number n is any integer, all the multiples of n times k, this is a subgroup, so we call it n times capital Z, because it's n times whatever element of Z you want. Right? If I add two elements of this thing, if I add two multiples of n, I stay a multiple of n. And one of the most interesting things we studied, and most important things we studied when we talked about divisibility and this number n, were its congruence classes. So how do you build a congruence class from this subgroup? Well, you just sort of add an element L to it, right? The congruence class of L, well, we defined it in another way, right? It was the set of all elements such that L minus that thing is divisible by n, but we showed that it's just L plus any multiple of n, right? So this is a common notation you'll see, that you take L and then you add any element of this set, and this set is any multiple of n. So this is some very compact notation for this set here. Okay. So how do we generalize this idea of a congruent class to a general group and a general subgroup? Right here, the subgroup we were looking at was n times z, and I had an element n, and I built some sort of translated version of the subgroup. And in general, this is called a coset. So if you have a general group and a subgroup H, a coset of that subgroup H is always determined by some element little g, and it's just what happens when I translate this set H by G, right? So it's all of the things which are G times H, where H comes from here. So one remark before we go through some examples of cosets is that for abelian groups, it doesn't matter, right? If I put G times H, it's the same as H times G. But for generally, you have to distinguish between left and right cosets. And the convention is usually that whenever you talk about a coset, you're always talking about a left coset. But you can also discuss right cosets. And the theory for right cosets is basically identical to the theory for left cosets. It's just a convention in terms of which side you want to multiply on. So this is what a coset is. So let's do some examples of computations of cosets. So here's an example. We have this group H, which is a subgroup of S3. You can check that the identity times each of these two is again this two. The identity acting on each of these is the same. I'm just checking closure under multiplication here, right? This squared is this. This times this is the identity. And this squared is this. Right, so this is the subgroup that is only allowed to move around in circles. Either I go around this way or I go around this way. I'm not allowed to reflect across axes. So what are the cosets of this subgroup? Well, what can I do? I can multiply H by the identity. You always have the identity coset, which is just H, again. And let's just check what happens when I multiply it by another element of the coset, 1, 2, 3. Well, if this was an element of the subgroup itself, the subgroup is closed under multiplication. So one of the things you can check is that this is equal to H, again. Right, 1, 2, 3 times the identity is 1, 2, 3. This times this gives me the identity. And this times this gives me 1, 3, 2. So I get every element of H by multiplying by 1, 2, 3. Let's try another one. 1, 2 times H. Well, this is identity times 1, 2 is 1, 2. 1, 2 times 1, 2, 3. Let's see what happens. Well, let's just write it like this first. All right, I just need to multiply each of the elements of my group by 1, 2. My subgroup, rather. So 1, 2, let's just put it in cycle notation. So here 1 goes to 2 and 2 goes to 1, so 1 is fixed. 2 goes to 3 and 3 is fixed. And then 3 goes to 1 and 1 goes to 2, so 3 goes to 2. So this is just another swap. And finally here, 1 goes to 3 and 3 is fixed. Right, 3 is fixed by this, so the total output is 3. 3 goes to 2, 2 goes to 1, so 3 goes back to 1. And then 2 goes to 1, 1 goes to 2, 2 is fixed. So the coset of H under this one, under 1, 2, is just these three elements, the three transpositions in S3. And we could continue. Let's do one more. Right, 1, 3, 2 for similar reasons is just going to give me back H. Let's see what happens when I do 2, 3 times H. And what we should get is this same coset. The important thing is the cosets are just sets. They're not sets with an order. So, okay, so 2, 3, I multiply by the identity, I get 2, 3. 2, 3 times 1, 2, 3. 2, 3 times 1, 3, 2. So what happens here? 1 goes to 2, 2 goes to 3, so 1 goes to 3. 3 goes to 1, 1 is fixed. And then 2 goes to 3, 3 goes to 2, so 2 is fixed. 1 goes to 3, 3 goes to 2, so 1 goes to 2. 2 goes to 1, and 1 is fixed, so 2 goes to 1. And then 3 goes to 2, 2 goes to 3. Everything is fixed. Okay. And you could also check that 1, 3 is also going to give me the same coset. 1, 3. All of the in a different order, of course, right? Each of these things will appear in a different order if I use the original ordering. But all three of these things gives the same cosets. And as we'll soon see, this is not a coincidence. And let's prove the theorem. So this is our first theorem for the day, that if you have a subgroup and you have two different cosets, then either they never intersect, so they're disjoint, or they're actually just the same coset. So it's exactly this picture, right? The cosets either give me H, or they give me all the things that are not in H. Right, so there are exactly two cosets in this example. There won't always be two cosets. But what is always true is that the cosets are either disjoint or they're the same. So let's prove it. So H is a subgroup. So proof. So I want to prove this dichotomy. So one of the ways to prove it is to assume that this is not true and then conclude this. So I assume that there's something in the intersection, and then I want to prove that these two cosets are actually the same. And now I want to prove actually that A times H is equal to B times H. So what we'll show actually is that A times H is a subset of B times H. And then the opposite inclusion will follow from a symmetric argument. So I just swap the roles of A and B and prove that B times H is a subset of A times H. So what do I want to do? I want to take an arbitrary element of A times H and prove that it's a subset of B times H. So what does an element of AH look like? Well, it's A times some H. So H belongs to H. And really, I should do it like this. I should choose H and H so that A times H belongs to A times H. This is sort of the more proper way to set it up. Now what do I want to do? I want to try to change this A into a B. Now so far I haven't used my assumption at all. My assumption is that this intersection is non-empty. Since AH intersect BH is non-empty, there's some K in the intersection. So K is A times H1, and K is A times H2, is B times H2, sorry, for some H1 and H2 in H. right? What's the definition? The definition of belonging to the intersection is that K belongs to each of these sets. So if K belongs to this coset, then K is equal to A times something in H. And if K belongs to this coset, then K is equal to B times something in H. They don't have to be the same element, but they do both have to belong to H. Now what happens? Well, this is the same element K. Hence, A times H1 is equal to B times H2. Now, A times, this is the thing that I want to work with, right? So I just need to replace this A by B. So I just solve this for A. All right, I can multiply by on the right by H1 inverse. Now putting all of this together, A times H, little h, is B, I just plug this in for A, H2, H1 inverse, times H, little h. But this here is an element of H. This big product. So I didn't say that it had to be just one variable, one simple expression for an element of H. The coset of A is, or in the coset of B, is B times any element of H. So this is some element of H. So in particular, this belongs to B, capital H, the coset of B. And what have I shown? I've shown that if I take any element of the coset of A, it belongs to the coset of B. And as I said before, reversing the roles of A and B shows that any element of the coset of B has to belong to the coset of A. So the output is that once these sets are non-empty, so either there's nothing there, in which case I can't find this K to get my argument started, or these two cosets are the same. Once they overlap even once, they have to be the same set. Okay. So this is theorem 5.21. That the cosets, basically this has the cosets partition the space, and we'll formalize that later. But every element belongs to some coset because G times H is, G is always an element of G times H for any G. Excuse me. And this says that they're either disjoint or they're the same. So if I look at the set of all cosets, this should be a partition of G. Okay, so what's our next theorem? Our next theorem is that all these cosets have the same cardinality. Right? This is the identity coset here, the order of the group. And the cardinality of any coset is the same as the order of the group. So the cardinality of any two cosets is the same, just from the transitivity property of cardinality. So this is nice, right? I have a partition of my space such that every element of my partition, every set in my partition, which are these cosets, have the same cardinality. And this will be the main point in our proof of Lagrange's theorem, which is next. So how do I prove theorem 5.2.2? Well, I just need to provide a bijection between them. And what's the bijection? How do we define it? Well, if you give me an element of H, I just multiply it on the left by A. Okay, so how do I prove this is a bijection? Well, I can just prove it has an inverse. So G is going to be from the codomain of F to the domain of F. And I define G of an element K by A inverse times K. Right? Basically, I just cancel out the A inverse. And it's easy to check that F of G is the identity on AH. Right? If you plug in an element of AH into G, it goes back to H when I multiply by A inverse, and then I just take it back to the same element that I started with when I multiply by A. Right? Because A times A inverse is the identity. And a similar computation shows that G of F is the identity on H. So once you have a bijection between two sets, we know that they have the same cardinality. So, and once we have that any coset has the same cardinality of H, any two cosets are in fact going to have the same cardinality. Okay, so now we want to put all this together and prove our main theorem for the day, which is Lagrange's theorem. So what does Lagrange's theorem say? So the setup for Lagrange's theorem is that I have a finite group. So the order of G is finite. So it's like Sn, it's not Z. It's not like Z where you have infinitely many elements. You have some subgroup of G. So it's closed under multiplication and all of this stuff. It has the identity and it has inverses. So what do I know? I know that the order of G times, this is called the index. Of H in G. So this is the number of distinct cosets. Of H times the order of H. Right, so what's the picture here? Well, let's go back to our example, right? I had S3. Well, I had this subgroup. So here was H. Here was 1, 2 times H. Here's one of my cosets, the only other coset. These two things have the same number of elements. So the order of H is twice the number of cosets of H times the order of H. So this was H, a subset of S3. Let's try another one. Let's try 0, 3, 9, which is a subset of Z9. In fact, let's do Z12. Well, here's my subgroup H. Call it H again. Has these sets 0, 3, 9. Right? 6, 9, sorry. What am I doing? 0, 3, 6, 9. This is now, it wasn't a subgroup before, but now it is a subgroup. It's just all the multiples of 3, right? So if I add any 2 multiples of 3, I get a multiple of 3 again, even if I'm in Z12. And it's exactly because 3 divides 12. Normally I would need to check what happens when I wrap around, but when I start, this is in fact the cyclic subgroup generated by 3. Let's use the notation that we developed last time. It's 3, 3 plus 3, 3 plus 3 plus 3, and then once I get to 4 times 3, then I wrap back around. So now let's check what the cosets are. Well, I can add 1 to it. 1, 4, 7, 10. And the group operation here is addition, so I'll write it like that. I can add 2 to it. So 2, 5, 8, 11. 2 plus the coset of plus the cyclic subgroup generated by 3. Then once I add 3 to it, then I wrap back around. So indeed, what's going on in Lagrange's theorem? These are my cosets. I have 3 distinct cosets. And each coset has 4 elements. The same number. So the total, how do you compute the size of something that's a rectangle like this? It's the base times the height. Right? The order of G times the number of cosets. And that's going to be our proof, basically. That's going to be our proof. I hope these 2 examples illustrated what's going on in this theorem. Okay, so how do we prove it? Well, I do exactly that. We'll define a bijection. Well, let's set it up first. So let C denote the set of cosets. Right, so in this case it would be, C would be 0, 3, 6, 9, 1, 4, 7, 10, 2, 5, 8, 11. All right, so I have in fact, let's call it C tilde. So this is a common trick you'll see. If you start running out of letters and you want to build an associated set from a set you start with, you can call the bigger set C tilde. So C tilde is the set of cosets of H. So for each coset in C tilde, choose one element called the representative. And let C be and C be the set of chosen representatives. So this should bring us back to what we did when we talked about modular arithmetic, right? Let me find the slide here. So if you remember, we had our collection of cosets, which we called L sub n, right? So we had our congruence classes. But when we do arithmetic in Zn in practice, we don't actually use this notation. We just pick the representative that's between 0 and n minus 1, right? One of the things we showed is that every such congruence class has a unique representative from 0 to n minus 1. So now we're doing the same thing in an abstract group theory setup. We have our set of cosets instead of congruence classes, and from each one, I'm picking a representative. So it might be 0, 1, 2, or E and 1, 2. Right, and basically what I want to do is we'll prove that the function f, which goes from C cross H to G, defined by f of CH equals C times H, is a bijection. Once this is a bijection, the order of G, which is just the cardinality of G, well, the cardinality of G is if this is a bijection, this is just the cardinality of C cross H, which is the cardinality of C times the cardinality of H. And what's the cardinality of C? Well, for each coset, I chose a representative. So how many cosets are there? Well, this is what we defined as the index of H and G. So this will prove the theorem if we can prove that H is a bijection. Right? Basically what we're doing is we're reconstructing these pictures for an arbitrary group. So now I want to prove that F is a bijection, right? The claim here is that when I do this picture, I get everything in my group G, as long as I've listed all of my cosets. So here we can't provide an inverse, but we will just prove directly that it's both injective and surjective. So let's prove injectivity first. So what do I want to do? I want to suppose, what does injective mean? It means that two points in my domain, which is C cross H, are mapped to the same value in G. So f of C H1 is equal to f of C2 H2. Then C1 H1 equals C2 H2, just by definition of F. So in particular, C1 H intersect C2 H is non-empty. Right? Because whatever this element is, C1 times H1, whatever the image is, this element belongs to C1H, because it's C1 times some element of H, and this element belongs to C2 times H, because it's some C2 times some element of H. So because they're the same element, they lie in the overlap of these two cosets. And what did we show? We showed that that means that these two cosets are the same. But for each coset, I chose a unique representative. I only chose one element for each such coset. One representative. I know that actually C1 has to equal C2. And once C1 equals C2, I can cancel it from, I can multiply by C1 inverse and get that H1 equals H2. Right, I can plug in C1 over here and cancel on the left, multiply by on the left by C1 inverse. So if f of C1 H1 equals f of C2 H2, then C1 equals C2 and H1 equals H2. And this proves injectivity, that there's no 2 points that are the same thing. Okay. So now I just need to prove in surjectivity. So I want to prove that for every little g and capital G, I can find some C and some H such that G is equal to that thing. So what's the trick? Well, it's again this thing. I can build a coset whenever you give me an element G and G. So GH is a coset by definition. Since every coset has a representative, I can find some C in C such that C times H is equal to G times H, right? These two cosets are the same. Because once the two cosets intersect, they must be the same. So I can choose a representative from the coset, right? This G times H has some representative C. Now C times H is equal to G times H. And what do I do then? It's clear, right? Since E is an element of H is a subgroup, G times E, which is G, is an element of G times H, which is C times H. So G is an element of C times H. So G is C times little h for some little h and capital H. And just by definition of F, G is F of C H. And that's the end of the proof. We built a function from this direct product space that just has sets, right? I have the set of representatives of each coset times the subgroup itself, and I wanted to build a function from this set onto G, which is a bijection. And once it was a bijection, we were able to conclude this product structure for the order, right? The order of G is the order of H times the index of H and G, the number of distinct cosets. And then once we had this reduction, the proof just became prove that the function is bijective. So prove it's injective and prove it's surjective. So this was our main theorem for the day, Lagrange's theorem. So how is Lagrange's theorem useful? So application. Here's just an easy application. There is no subgroup of even order in Z21. Right? Because once the subgroup had even order, that would imply that the order of G was also even, because it would be something times the order of that subgroup. So no matter how hard I try, when I look at the subgroups of Z21, or really Z any odd number, you can't find a subgroup of even order. So in fact, every subgroup must be of order 1, 3, or 7. 7 or 21. These are the only possible orders of subgroups in Z21. So it narrows down what you have to check very, very quickly. And there's a lot more structural things that sort of come out of Lagrange's theorem. Okay, so I think I'll stop there for today. Tomorrow we'll talk more about application, or not tomorrow, but Wednesday we'll talk more about applications of Lagrange's theorem and getting what we want out of it. Yeah, this is sort of one of the pinnacles of finite group theory. The first non-definitional theorem. Everything we've proved about groups so far has just been checking definitions and sort of putting them together and building technology. We haven't really gotten any big structural theorems yet. And this is the first big structural theorem. We've gotten a lot of structural theorems specifically about the symmetric group, but about finite groups in general, we haven't gotten anything. So this is the main result there. Okay, so thanks for listening. I will see you on Wednesday. Bye-bye.